this lesson, we'll introduce the concept of portfolio management. We'll discuss the computation of expected returns and risk of a portfolio. We'll discuss the concept of portfolio construction with two security case and multi-security case. Lastly, we'll examine the concept of risk diversification with portfolios. Portfolio construction with two securities, expected returns. Till now, we have understood the interpretation of expected returns for a single security case. Now we'll discuss expected returns for a portfolio of securities. Let's start with the portfolio construction for two securities. Some of the important questions that we are trying to answer is what is a portfolio and why to invest in it. More specifically, what happens when you invest in a portfolio, what happens to your expected return, and what happens to the risk when you combine two securities or multiple securities in a portfolio. What is this term called diversification? What are the benefits of this diversification? Also, what is investing in mutual funds and indexes and how they provide diversification? Lastly, what is the difference of investing in a portfolio like Nifty 50 versus a single stock like HDFC? What are the risks involved? How they are fundamentally different from each other? Let us consider a portfolio of two securities where the actual returns from the two securities are R1 and R2. Also, if the proportionate weights or amounts invested in these securities are W1 and W2, then W1 plus W2 equal to 1 because the entire amount is invested in the portfolio, so the summation of all the weights have to be 1. We already know that expected return on security 1 expected or ER1 equal to R1 bar and expected return on security 2 ER2 is R2 bar. Now let's try to understand the return from the portfolio. The actual returns from portfolio can be very easily computed as shown here in equation 1 where Rp equal to W1 into R1 plus W2 into R2. That is a very simple mathematical notation for the actual returns from a portfolio with two security case where W1 and W2 are the proportionate amounts and R1 R2 are the actual returns observed on these two securities. Now let's try to understand the expected returns for this portfolio. The expression for expected return on portfolio Rp can be written as ERP equal to expectation of W1 R1 plus W2 R2. Or we can further expand this result as expected value of W1 R1 plus expected value of W2 R2. Please note here W and W2 are constant which are fixed from outside, from the investing side. So we can take them out and therefore the resulting expression becomes W1 into expectation of R1 plus W2 into expectation of R2 as shown here in the equation 4. Please note here that R1 and R2 are probabilistic random variables with finite distributions. Generally, such distributions are approximated by a normal distribution. And therefore, these random probabilistic variables which are returns, for them expectations can be computed. For example, the expected return on security 1 R1 is R1 bar. Similarly, expected return on security 2 is R2 bar. And if the weights, investment weights are known, that is W1 and W2, the expected return on portfolio can be computed as Rp bar equal to W1 times R1 bar plus W2 times R2 bar. So therefore it appears that expected returns from the portfolio are simply the weighted average of expected returns of individual securities in the portfolio. We are able to achieve this result simply because R1 and R2 being random probabilistic variable, their expectations can be easily computed as R1 bar and R2 bar. Now, this result can be easily generalized for a 3 security case or even multi-security case. Let us consider a simple 3 security case where the entire amount or entire wealth is invested in 3 securities R1, R2, R3. The proportionate amounts are W1, W2 and W3 and therefore the summation of W1, W2, W3 should be 1 because this is the total amount of wealth. And W1 amount is invested in security 1, W2 amount is invested in security 2 and W3 is invested in security 3. Therefore, when we generalize our previous result, RP bar equal to W1 times R1 bar plus W2 times R2 bar plus W3 times R3 bar. This can be further generalized to an n-security case where proportionate amounts, that is W1, W2 and so on up till Wn, are invested in securities 1, 2, 3 and so on up to security n respectively. Also, the summation of all these Wi should be equal to 1, which is the total amount of wealth invested. And generalizing the result, total expected returns on portfolio RP bar equal to summation I equal to 1 to capital N Wi times Ri bar, where Wi's are the weights and I bar are the expected returns on security I. To summarize, in this video, we discussed the expected returns on a portfolio of two securities, which comprises simply the weighted average of returns on those two securities, weights being the proportionate amount invested. We arrived at the formula for these two securities, and then we generalized this case for a multi-security case where securities 1 to n securities are there, and the expected return on that portfolio is simply the weighted average amount of proportionate amounts invested in all these n securities, which is multiplied by the expected returns on all these n securities, which is Wi times Ri bar summation I equal to 1 to n. Expected returns from portfolio, a simple example. In this video, we'll talk about expected returns from a portfolio with equal probability case and case with different probabilities. Let us start with the expected returns from portfolio case 1 with different probabilities. On column 1, we have probabilities that are shown here. These are the probabilities for different scenarios. Corresponding returns for security A are provided here and corresponding returns for security B are provided here. The weights are fixed externally, 40% investment, proportionate investment in security A and 60% proportionate investment in security B. Now, the actual returns for each scenario are computed here, which are simply WARA plus WB by RB. And this will give us the actual return for each scenario with given probabilities as shown here. Now we can multiply each probability with the return scenario, that is PT into RP. For example, 0.2 into 7.2%, which is 1.44%. Similarly, each probability can be multiplied with corresponding return to get PT into RP. And when we add this all up, that is P1 into RP1 plus P2 into RP2 till P6 into RP6, we get the expected return on portfolio RP. This is expected return on portfolio RP, which is 8.65%. This was the case where all the associated scenarios have different probabilities. Let us consider another case where all the possibilities are equal. That means all the scenarios have equal probabilities, and if let's say we have n possible scenarios, then each scenario will have 1 upon n probability. In this case, since we have 6 possible scenarios, each scenario will have 1 by 6 probability. And therefore, to start with, we have the corresponding returns. Weights are externally fixed. So first we'll compute the return from portfolio for each scenario, which is WA into RA plus WB into RB. So for first case, it is 7.2%, which is 9% into 0.4 plus 6% into 0.6, and WARA, which is 3.6%, WBRB, which is again 3.6%, and the overall figure works out to 7.2%. In the similar manner, we'll compute the actual returns for all the possibilities, all the 6 possibilities, and the summation works out to 8.43%. The average of this summation works out to 8.43%. That means we sum up all these return numbers and then take the average, which is 8.43%, which is the average of all these 6 return figures, and that becomes our expected return for equal probability case, where all the probabilities are equal. To summarize, in this video, we discussed how to compute expected returns for a portfolio when case 1, given scenarios comprise different probabilities with each scenario, and case 2, a scenario where all the possibilities or all the scenarios have equal probability. Portfolio construction with two security case risk. In this video, we'll try to understand the risk of a two security portfolio. Till now, we have already understood how to compute the variance of a security for a case with given probabilities. Kindly have a look at this formula. Here, if the probability of different return scenarios is PTs, that is P1, P2 and so on up to PT, and different returns, that is RI1, RI2 and so on as a generic term RIT, then the variance of that security can be easily computed as PT into RIT minus RI bar raised to the power 2 summation over T equal to 1 to T. This is a very simple and standard formula for computation of variance for a security with different probabilities. Now, if the probability or the probability of observing each observation is equally likely, then in that case, P1 equal to P2 equal to P3 and so on up till PT. We also know that summation of Pi is equal to 1. In that case, this becomes 1 upon T. So if there are T observations and all of them are equally likely, then all of them becomes 1 upon T. In this case, the variance of the security can be easily computed with this formula, summation RIT minus RI bar raised to the power 2 upon T. In some of the textbooks, they also note that since we are working with samples, instead of using T, they would be using T minus 1. Here, instead of using T, they would be using T minus 1. Now, let us consider the variance or the risk of a two security portfolio. In the case of a two security portfolio, let's remember the very simple formula for A plus B raised to the power 2, which is A square plus B square plus 2AB. The risk of a two security portfolio can be very easily extended or understood in this with this help of this formula, which is sigma P square is W1 sigma square, which is corresponding to A square, then W2 square sigma 2 square corresponding to B square. And for 2AB, we have a term very similar, which is 2 times W1 sigma 1 plus into W2 sigma 2 into rho 1 2. Now here this extra term of rho 1 2, rho 1 2 here is the correlation between security 1 and 2, has some special meaning as we'll see shortly. Here sigma P is the standard deviation or a proxy of risk for the portfolio. Sigma 1 and sigma 2 are the standard deviation of individual securities. W1 and W2 are the proportionate amount of investment in each of these securities. We already know if the portfolio carries only two securities, then W1 plus W2 should be equal to 1. These are the proportionate amount invested. And importantly, rho 1 2 is the correlation between these two securities. This correlation varies from -1 to +1. Now we'll try to understand with different scenarios what if this rho 1 2 is equal to 1 or 0 or -1. Let's start with a very simple scenario where this rho 1 2 is equal to 1. Again, the formula of the portfolio risk is already known to us, which is sigma P square equal to W1 square sigma 1 square plus W2 square sigma 2 square plus 2 times W1 W2 rho 1 2 sigma 1 sigma 2. Now please note here this expression rho 1 2 into sigma 1 sigma 2 is also called the covariance between the securities 1 and 2. And here rho 1 2 is equal to rho 2 1, and that is why you have a multiple of 2. In case this rho 1 2 or rho 2 1 equal to 1, then this formula considerably simplifies to sigma P square equal to W1 sigma 1 plus W2 sigma 2 raised to the power 2, which is again, remember, coming from the A plus B raised to the power 2 formula, which was equal to A square plus B square plus 2AB. And in this case, the sigma P works out to W1 sigma 1 plus W2 sigma 2. Please note for all the values, and we already know that this rho 1 2 lies between -1 to +1. So the magnitude of this rho 1 2 will always be less than 1. And therefore, for all the values of rho 1 2, they will be less than 1. They starting from -1 to +1, they'll always be less than 1. And therefore, for all the other values of rho 1 2, the value of risk sigma P will be less than this quantity. Whatever it may be, it will always be less than this quantity. What are the implications of this? Please understand that if the securities have perfect correlation, that means they are perfectly moving in lockstep, and therefore their correlation is 1. There is no diversification, and portfolio risk is also very similar to the portfolio expected return, similar to what we computed for expected return, that was weighted average. Portfolio risk here is also the weighted average of risk of these two securities. For all the other cases where this correlation is less than 1, and we noted this is a maximum correlation case, which is rho 1 2 equal to 1. For all the other cases, this sigma p will be less than the weighted average of individual risk components multiplied by the proportionate weights, and this reduction in risk is precisely what we call as diversification in risk. Where are we getting this diversification? This diversification is appearing because the correlation between these two securities is less than 1. That means any correlation which is less than 1 results in diversification. Let's consider another extreme case where correlation is equal to -1. In this particular case, again, our good old formula of sigma p square equal to w1 square sigma square plus w2 square sigma 2 square and so on, w2 times w1 w2 rho 1 2 sigma 1 sigma 2 considerably simplifies to this formula. Now in this formula, if we further solve this expression, we will achieve this. This is a very special case for a correlation of -1. What are the implications of this formula? Please notice, although the correlation of -1 is usually not observed in financial markets or other commodity and derivative markets, it leads to a special case where a particular W1, W2 can be achieved where this value can be made 0. But please note, this is only theoretical discussion, because in no financial markets or between two securities, negative correlation is observed over medium to long terms. And therefore, from theoretical and academic discussion purposes, assuming that sigma rho 1 2 correlation equal to -1, in that case, a particular combination of weights can be achieved where sigma p becomes 0. This is a more of a theoretical case, but it suggests that a particular scenario can be obtained theoretically where the overall risk can be made 0. This is the case where maximum diversification is achieved, where sigma p becomes equal to 0. The risk of the portfolio becomes 0. Now let us understand a more generic and easy to use thumb rule while constructing the risk for a two security portfolio. You need to create 2 cross 2 boxes like this, where you have first W1 sigma 1, W2 sigma 2 here, and W1 sigma 1, W2 sigma 2 here. Now in the first box you will combine these two terms to get W1 square sigma 1 square, and again this cross term will give you W2 square sigma 2 square in a very similar manner. So these are called diagonal boxes. If you look at off diagonal boxes or boxes that are opposite to the diagonal, you will combine W2 sigma 2 with W1 sigma 1 and you get W1 sigma 1, W2 sigma 2. But in addition to that, you also get a correlation term which is rho 1 2. Similarly, in this off diagonal box, you combine W2 sigma 2 with W1 sigma 1 to get W1 sigma 1, W2 sigma 2 with again correlation term. And if you add up all these four terms, you get that generic expression that we saw earlier. W1 square sigma 1 square plus W2 square sigma 2 square plus 2 times W1 W2 rho 1 2 into sigma 1 sigma 2, which was our generic expression that we used earlier to compute the risk of two security portfolio. To summarize, in this video, we understood how to compute the risk of a two security portfolio. We also understood that securities that move exactly in lockstep manner with a correlation of 1, there is no diversification, and maximum diversification is achieved when the securities move exactly in opposite manner, that is with a correlation of -1. For all the other cases, correlation remains less than 1 and some amount of diversification is always achieved when two securities are added. Portfolio construction with multiple securities. Risk. In this video, we'll extend our understanding of portfolio risk for a multi-security case. Let us start with a portfolio of 3 securities. We'll extend our logic that we developed in the previous video for two securities case. We'll try to implement that here for multi-securities. Simply extending the formula for a two security case to multi-security case, kindly have a look at this 3 cross 3 box. And we'll try to extend this formula that we developed there for this 3 cross 3 security case. So we have W1 sigma 1 for security 1, W2 sigma 2 for security 3, W3 sigma 3 for security 3. Similarly, we have rho 1 2 for correlation between security 1 and 2, rho 1 3 for correlation between security 1 and 3, and then we have row 2, 3 for security 2 and 3. Now, the overall portfolio risk will be a combination of these diagonal terms, that is W1 square sigma square, very similar to what we did earlier for two securities, then W2 square sigma 2 square, W3 square sigma 3 square. And again, the off diagonal terms that are here, they will be put together, W1 sigma 2, sigma 1, W2 sigma 2, and along with that, there is a correlation term rho 1 2. Similarly, if you look at this particular box, here you are combining W1 sigma 1 with W3 sigma 3. So this term will result, and then in addition you are putting correlation term, and this goes on for all the non-diagonal or off-diagonal boxes like this and this. Each of these non-diagonal boxes, they will include a correlation term, because here we are combining the variance of two different securities. Unlike diagonal terms where we have same security and the variance term was computed. Let us extend this understanding to a more generic n security case. Here again you have W1 sigma 1, W2 sigma 2 and so on up till Wn sigma n, and W1 sigma 1 here on the column and row side. As you would have already guessed, these diagonal boxes will include all the variance term that are combination of W1 square sigma 1 square, W2 square sigma 1 square. So this will be something like W1 square sigma 1 square and so on, so up to Wn square sigma n square. So these are all the diagonal boxes. On the off diagonal terms, you will have combination of two different securities. For example, here you have W2 sigma 2, W1 sigma 1 along with the correlation terms. Similarly, here you will have W1 sigma 1 Wn sigma n along with the correlation term rho 1 sigma rho 1 n, and so on and so forth up till here, where for example you may have something like Wn minus 1 sigma n minus 1 into Wn sigma n and a correlation term between security and n minus 1. So in this fashion we will fill all the off diagonal terms, which will include the covariances between two different securities, these off diagonal boxes, while the diagonal boxes like this, they will include only the variance terms. Now let us understand the variance of this n security portfolio, and let us focus on the diagonal terms. So how many diagonal terms we observe? There will be n into n, that is n squared terms, while out of these n squared terms, there will be n diagonal terms, and these diagonal terms will carry only variance terms like sigma I square, wi square. So if I sum up all these diagonal terms, something like sigma I equal to 1 to n summation wi square sigma I square will result. This is because all those diagonal terms, if you notice this diagram here, all these diagonal terms, there are n such diagonal terms, and all these diagonal terms will include an expression like W1 square sigma 1 square or Wn square sigma n square. So if I add up all these diagonal terms, an expression like this will emerge. Now, to simplify the situation, let us assume that all these securities have equal investment, that is 1 by n proportion. That means since there are n securities, and if I invest equal amount in each security, the proportionate amount invested in each security will be 1 by n. With that assumption, my Wi, which is equal to 1 upon n, and therefore Wi square will become 1 upon n square, and therefore a term like this will be simplified into this. Now let us take this 1 upon n outside the expression. So we are left with this. Please note here n is not the varying term, only I subscript is varying, so we can take the n outside, and here Wi is 1 upon n. So we get something like this expression inside, which we can define as average variance. So if let's say define average variance as something like this, so we'll have something 1 upon n into average variance term, which is defined simply like this. So our overall variance for the portfolio becomes 1 upon n times sigma square average, where this is average variance term defined as this. Now let us focus on the off diagonal boxes. As we noticed that there are total n square boxes and n are the diagonal boxes, so we are left with n square minus n off diagonal boxes, which include covariance terms or the cross products of securities, including the weights invested in these securities, and the resulting term, we have already seen this, that will appear something like Wi Wj sigma I sigma j into rho ij. So these are our off diagonal terms. Now the overall multiplication will appear something like this. If I sum up all the covariance terms of diagonal terms, all those n square minus n terms, I'll end up with something like this. Wi Wj sigma I sigma j rho ij summation I equal to 1 to n summation j equal to 1 to n where I is not equal to j. Why this special subscript? Because for all the cases where I equal to j, they will become the diagonal terms with variance terms. Now we already made a simplifying assumption that Wi equal to Wj equal to 1 upon n. That means we are investing equal amounts in all the securities, and therefore those proportionate amounts Wi equal to Wj are same as 1 upon n. In that simplifying case, our overall expression becomes this: 1 upon n square into sigma I sigma j rho ij. We can take n out of this expression because n is constant, so we are left with this expression. Now let us define an average quantity of covariance or average covariance. We already know that there are n square minus n boxes or n into n minus boxes. So an average covariance can be easily defined something like number of or summation of all these covariance terms divided by total number of these covariance boxes, which are n into n minus 1 or n square minus n. So let us define our average covariance as we did for variance terms also. We can define our average covariance as total number of boxes or total number of terms, which is n into n minus 1 multiplied by summation of all these covariances. So this is our average covariance or a simplifying assumption. Now let us rearrange these covariance terms a little bit. We already defined that summation of all these covariance terms is this, which further simplified to this. And we defined something called average covariance like this, which is 1 upon n into n minus 1 times the summation of all these covariance terms. Now let us rearrange them a little bit. So here I can take the n square from this expression to this side. So my summation of all these terms is equal to covariance terms into n square. Now here I already know that this expression is equal to, because of this expression is also same as sigma average covariance times n into n minus 1. So this is equal to this because of this expression, and we already defined that summation of these covariance terms is equal to this one, where n square we can take here. So a very simple expression, summation of all these covariances becomes this covariance term summation into n square, which is equal to again sigma average covariance time n into n minus 1. And therefore what we are interested in is the summation of all the off diagonal terms or the risk of off diagonal terms, which is covariances, which simply becomes n square into n minus n, which is this, into 1 upon n square into sigma square average covariance, because we can take this n square here, and therefore the equality becomes very simply n square minus n into 1 upon n square times sigma average covariance, or more simply n minus 1 upon n into average covariance. Now that we have a simplified expression for covariance as well as variance terms, let us put this expression together to find the overall risk of the security. So first we have set of variance term for which we found a simplifying expression in the form of average variances. So our simplified variance terms is equal to 1 upon n times sigma square average, and our covariance term summation is equal to n minus 1 upon n into average covariance. So we'll put them together to find the overall risk of the portfolio, or sigma p square, which is 1 upon n into sigma square average plus n minus 1 upon n into average covariance term. Now if you have large number of securities, fairly large number of securities where n is tending to infinity, for practical purposes you do not need to go up to infinity. Even with 20-30 securities, a reasonable amount of diversification is achieved. So theoretically, if n is fairly large, please notice that this term will approach to 0, because here denominator is n, while if n tends to infinity, this term will approach to 1, and therefore we can easily say that when the n value is sufficiently large or tending to very large values, the variance term or the diagonal terms will come 0. So the overall portfolio risk or portfolio variance will be simply equal to the average covariance, and all the variance terms are cancelled out because of this property that n is fairly large, and therefore this term will approach to 0 and this term will approach to sigma average covariance or average covariance of the portfolio. What are the implications? So here we find that just by adding a sufficient number of securities, we can cancel out or neutralize the idiosyncratic or stock specific or variance part, the diagonal terms that were there. They are cancelled out, while the average covariance term that is not nullified, and therefore the overall portfolio risk tends closer to the average covariance term. This is precisely what we achieve with the help of diversification. Simply by adding more and more securities, we achieve or neutralize the idiosyncratic or variance terms that are stock specific equal to 0. To summarize, in this video, we discussed how addition of securities neutralizes the stock specific or variance terms or diagonal terms part of risk. These are the variance terms, and as we keep on adding security, the off diagonal terms, which include covariances, they are not neutralized, they still remain, and therefore the portfolio risk tends towards this average covariance for a large number of security portfolio. We also discussed how to extend our logic of two security portfolio to generate expression for multi-security portfolio, and how this multi-security portfolio with reasonably large number of securities achieves diversification. Risk diversification with portfolios. In this video, we'll conclude our discussion on risk diversification with portfolios with the help of a few numerical examples. Now we have understood that in a portfolio with large number of securities, the summation of variance term is close to 0. For example, if we start with a portfolio with one security, like in the diagram shown here, a large part of the portfolio risk comprises security specific or idiosyncratic risk, which is driven by the variance terms, the diagonal terms that we saw, which are variance terms. However, as we keep on adding more and more securities, this particular component, this variance or idiosyncratic or stock specific component of risk, tends to become nullified or cancelled. In contrast, there's another component of risk which is on account of covariances, that is correlations across securities. This component of risk is, even though it is small in a single stock portfolio, as we keep on adding more and more securities, it is not diversified or nullified in the portfolios. So as we keep on adding more and more securities, this component remains still, and for a very large number of securities, only this part of portfolio risk remains, while the specific or idiosyncratic risk tends to go down to 0. And the remaining component, which is this average covariance risk, this is also called bedrock of risk, as it cannot be eliminated by adding more and more securities. The diversification is achieved only because of cancellation or neutralization of this stock specific risk. We also noted that this average covariance risk, or risk that is on account of those off diagonal terms or covariances, that is driven by the correlations across securities. Now, if we want to further decrease the risk which is driven by these covariances, we would like to select securities that have low correlations with each other. As you keep on adding more and more securities in a portfolio, like we discussed, this specific risk is almost close to 0. And if you add all the securities available in the market, the overall risk that is remaining will only constitute this risk that is driven by these covariances. And often it is called market risk or bedrock of risk, because that portfolio with all the securities available in the market, the risk which may be called as market risk is driven by these covariances and often referred to as market risk or bedrock of risk. This is also called systematic risk or non-diversifiable risk, because it cannot be diversified by adding more securities. In contrast, the specific risk, that is called diversifiable risk or non-systematic risk, because it can be diversified simply by adding more securities to the portfolio. In financial markets, fund managers and investors are only rewarded for bearing this market risk. Often you would have heard the statement on mutual fund ads that mutual funds are subject to market risk. The statement precisely reflects this fact that this risk cannot be eliminated. Even if you add all the stocks and securities available in the market, you would still be exposed to this systematic risk or market risk, and this cannot be diversified, and therefore markets only reward for bearing this market risk or systematic risk. Therefore, as we'll see shortly, number of asset pricing models, they price this market risk only. They do not price this specific stock specific idiosyncratic risk. They only price this market risk, and therefore fund managers and investors are rewarded only for bearing this market risk component. Let's perform a simple example of expected portfolio return. Let's say if you have two securities, you invest 60% of the money or wealth available with you in security 1 and 40% of the wealth in security 2. Now you also know that expected returns from security 1 and 2 are 8% and 18.8% respectively. Therefore, the computation of expected return, as we have already seen in the formula, is very easy, and it is simply W1 times R1 bar plus W2 times R2 bar, where W1 is 60, 0.6, and W2 is 40%, which is 0.4, multiplied by their respective returns, expected returns, which is 8% and 18.8%, and therefore we get 12.3% as expected return on the portfolio. A portfolio that comprises 40% of security 2 and 60% of security 1 wealth invested will give you 12.3% as expected returns. Let us consider in the previous example some additional information. That is, the risk of security 1 is 13.2% and the risk or sigma 2 is 31%. And the weights invested remain the same, which is 60% in security 1 and 40% in security 2. Now, for different cases, 5 cases in fact, with correlations of -1, 0, -0.5, 0, 0 and 1, let us try to compute the risk of the portfolios. We already know that the risk of a two-stock portfolio can be easily computed with the help of this formula, which is W1 square sigma 1 square W2 square sigma 2 square plus 2 times W1 W2 sigma 1 sigma 2. All the other quantities are fixed, and we are only varying this correlation from -1 to +1. Let us see how these numbers worked out. So first look at the first case where rho 1 2 equal to 1, and the formula is simply the same formula that we are using, W1 sigma square 1 and so on. And in this case, the overall risk works out to 20.32%, which is also same as the weighted average of individual risk. This is because now in this case, as we have seen with rho 1 2, no diversification occurs, and the formula is simply standard deviation or variance formula is simply this, because no diversification is there and securities are moving in perfect lockstep manner. Now, as we keep on decreasing the correlation using the same formula, please notice the portfolio risk or standard deviation comes down gradually, 17.74% for rho 1 2. Here the correlation number is 0.5. All the other things remain same. For correlation equal to 0, the standard deviation is 14.71%. For correlation is equal to 0 minus 0.5, the portfolio risk is 10.81%. Please note that the portfolio risk is minimum when correlation is -1. So this shows that as correlation decreases, more and more risk is decreased and diversification is achieved as the correlation is lower. To summarize, in this video, we discussed the two components of risk, which is one, which is stock specific and idiosyncratic component, or diversifiable risk or non-systematic risk. This component of risk can be easily nullified or neutralized by adding more and more stocks to the portfolio. Next, we also discussed the systematic or market component of risk, which cannot be diversified and it acts as a bedrock of portfolio. So even if you include infinite number of securities, this market risk or systematic component of risk cannot be diversified, and it will depend on the correlation across securities in the portfolio. We observe that as we keep on decreasing the correlation from -1 +1 to -1, we notice how standard deviation of the portfolio decreases. So in order to decrease the risk of portfolio, a well-diversified portfolio with large number of securities, if you pick and choose those securities where correlation is less than 1, you can achieve more and more diversification. To summarize this lesson, adding more securities that are less correlated or have lower covariance in the portfolio leads to diversification. Diversification here means the reduction of stock-specific risk. The part of the risk that is non-diversifiable is on account of the covariances across securities. Often, this risk is called market risk or systematic risk. Markets do not reward for bearing stock-specific diversifiable risk, since these risks can be easily mitigated and diversified. When we say that we expect certain return for bearing risk, That risk is systematic non-diversifiable risk, or often referred to as market risk.